Hi everyone, so today we are going to be having a look at conditional probability, which is as close as GCSE probability gets to A-levels. In fact, there will be one or two bits which could come up, so if any of you are thinking about maths A-level as well, I'll give you a bit of a flavour of the sorts of things we'll do for probability then. And it's when conditional probability is when it starts to get a little bit sort of more realistic to things that really happen, because it's very rare that any one event is totally independent of another, doesn't have an effect on it. Anyway, we will have a go at some of those today, and we will be solving them by tree diagrams help a lot, and sometimes Venn diagrams can too. But before that, we will have a quick look at the inequalities starter that I gave you last time. Right, so here's our puzzle from last time. And the first number I was able to put in was along here, because this one's bigger than that one, which is bigger than that one again. So that could go 2, 3, 4, but it can't be 4. It could go 2, 3, 5, except it can't be 5 because this number is also smaller than that one. So that means that this cannot be a 5. It cannot be a 4. Therefore, it must be a 3. So we've got 3, 2 and 1 there, which means we must have 5 in that row. Now, this number here is smaller than that one, which is smaller than that one. So this must be 3 and 4, because this is a 5 here, so it's got to be getting bigger as it goes. And if that's 3 and 4, then we must have a 1 here. It takes a bit more searching to find the next number, but eventually I know this cannot be a 1 because it's bigger than something. This is bigger than something, it cannot be a 1. This is smaller than, but it cannot be a 1 because it is below, it's in this column here, and we've already got a 1 there. So this is smaller than something, so this is the only one that can be a 1. And then I can continue looking at ones, because I know that this can't be a 1 because it's in that column, this can't be a 1, this can't be a 1, this can't be a 1 because it's bigger than other numbers, this must either be a 4 or a 5, so the only place in that row that a 1 could go would be there. So it's not about guessing, it's about looking for one which must go. We also have 4 numbers out of 5 there, so this has to be a 3. And the next one I can see is 5, because you can't have a 5 here in this column. Obviously you can't have a 5 there. You could have a 5 there. You can't have a 5 there because it's got to be smaller than 4. So that's got to be a 5. And if that has to be 5, this number here is bigger than a 2 or a 3, so it can only be a 4 or a 5, but it can't be a 5 because it's in that row, so that's a 4. Now we've got 4 out of 5 of this row, so there's only a 2 left that can go there. I know that 3 and 4 go either place there, not sure which one yet. Looking in this column, this one could be 1 or a 5. This can't be a 1 because of that and because it's bigger than something, so this must be a 5 and that must be a 1. And then we know that this number here has got to be bigger than 3. Well, it can't be a 5, so it must be a 4. And if that is a 4, then remember over here it had to be a 3 or a 4. This can no longer be a 4, it must be a 3, which means 1 to 5 up here, that must be a 4. And now up here we've got a 3 and a 5. Well, this number is smaller than 4, so it can't be 5, so it must be 3. So this is called process of elimination that we're doing now. And then in this row and this column, we're just missing a 2, which is smaller than 5. And we have completed it. If you think I've made any mistakes, please let me know. Okay, so just as before, we're going to be going through some of the mathsgenie questions, and looking at the first bit, it looks very, very similar to what we did last time, but there is a subtle difference. He's got 10 marbles in a bag, 6 of them red, 4 of them green. Mason takes one of them at random from the bag. but he then doesn't put it back and takes a second marble from the bag. Sometimes these questions say he just takes 2 marbles from the bag, and we can solve them in exactly the same way as if he took one and then another. So pause the video, have a little go at what you think would happen when you fill it out. So we've got 6 red out of 10. We've got 4 green out of 10. Definitely don't simplify these because it makes it harder to think about. If he has a red with the first one and doesn't put it back, he's only got 5 reds left, and he's only got 9 marbles altogether left. He still has 4 green ones left out of 9. If he had taken a green one first though, he would still have had 6 red ones out of just 9. And if he had taken a green the second time, it would have just been 3 out of 9. So that'd be 2 marks for filling that out. And then part B, you may have noticed at the bottom there, says work out the probability that Mason takes 2 marbles the same colour. So if you haven't had a go, stop the video and have a go at it now. So 2 the same colour means that one, and it means that one, not that one or that one. So we don't need to work those out, but we need to use and meaning multiply, to say he gets a red and a red, 6/10 times 5/9. 6 5s are 30, over 10 9s are 90. Do not simplify. And then we're going to need or, because it could be red or 2 reds or 2 greens, and or means add. 4/10 multiplied by 3/9. We're still going to have 90 as our denominator. 4 times 3 is 12. So that means the probability of getting 2 marbles the same colour are going to be 30 out of 90 for 2 reds, plus, less likely but still quite possible, 2 greens, 12 out of 90. Add those together, our denominator stays the same, and we go up to 42 out of 90. Now you may simplify it if you want to, but you don't have to. And if you had simplified it, you could have gone to 21 over 30, but that wouldn't be fully simplifying it. You can divide them both by 3, so 7/15 would have been fully simplified, but that is full marks. Question 2. Now part B, I'm just going to read out for you. If you haven't printed off the worksheet, it says work out the probability Paul wears different coloured ties on Monday and Tuesday. So pause the video, give it all a good go. You may use a calculator on this, by the way. So if he wears a black tie on Monday, the probability that he will wear a black tie on Monday is 0.6. So that means a red tie has to be 0.4 because he's only got black and red ties. Then if he wears a black tie on Monday, the probability to wear a black tie on Tuesday is 0.35. If he does not, and so if that's 0.35, the chance of him wearing a red tie has gone up to 0.65, so they add up to 1. And again, if he doesn't wear a black tie on Monday, the probability he will wear a black tie on Tuesday increases to 0.68. 68 plus 32 makes 100, so that'll be 0.32. And then we're looking at working out the probability he wears different colour ties. So that means he doesn't have black and black, he doesn't have red and red. We want this one or that one, which means work out that one and add it to this. So this is going to be 0.6 times 0.65. This is going to be 0.4 times 0.68, which gives us 0.39 and 0.272. And then all you've got to do is say, right, I've got my chance of the black and then red being 0.39. I'm going to add that to red and then black of 0.272. And that gives us 0.662. And if you did it as a fraction, that's okay, but generally when it's in decimals, stay in decimals. When it's in fractions, stay in fractions. Unless, if it had just been 0.6 and 0.4 all the way, then working in fractions may have been easier. I don't know. Okay, the next question hasn't got the structure of the tree in there for you. You're going to have to put it in there. So pause the video, read it all, give it a good go. There's 4 marks for the question. So we're taking 2 counters. So we have the first counter being, and you just, because it says it's at random, so we're going red and we've got blue, and we'll have 5/8 and 3/8. But if he takes 2 at random, then you can treat it as if he takes 1 and then the next. So the second one, there will only be 4 out of 7 left. And there will still be 3 blues out of 7. And similarly, there will only be 2 blues left if he's already had a blue out of 7, and there will still be 5 out of 7 there. Now we want the probability that 1 counter of each colour are taken, so not 2 reds and not 2 blues. So like the one that we had before, we then just need to multiply these together. Times 3/7 gives me 15/56, and we get the same numbers just switched around, so still giving us 15 out of 56. It doesn't matter if it's red then blue or blue then red, so we can say that we're going to add those 2 together, which is going to give us 30/56, and if you halve both of those to give you 15 out of 28, then that's fine too. Question 4 is very similar to the previous one. Read it carefully, pause the video, give it a go. One significant difference, of course, is the fact that there are 3 different colours of counter this time. But that does make it a little bit more complex, but it just means that at every point there are 3 things that can happen, 3 options, so we need to recognise those. So we've got red, blue and green, 5 out of 10, 3 out of 10 and 2 out of 10. And then he takes another counter, so that's the first counter from the bag, and the second counter from the bag, red, blue, green, red, blue, green, red, blue, green. Just set it up like that, and then we just need to remember that it's all going to be out of 9. And then we just need to take care about which one of the 3 each time has dropped 1. So the red has dropped by 1 here, whereas the others will stay at 3 and 2. The blue has dropped here, so the red stays at 5, the blue goes to 2, the green stays as 2, the green has dropped here, so the red stays as 5, the blue is 3, and the green drops down to 1. Now we want the probability that both of them are the same colour. So we don't want that or that, we do want red and red. We don't want blue and red, we want blue and blue. We don't want those, we want green and green. So there are 3 things that can happen. We add them all together after multiplying to get what we should have. So we've got 5/10 over 4/9. 5 4s are 20, 10 9s are 90. Next one, 3/10 multiplied by 2/9 gives us 6 over 90, and the last one, 2/10 times 1/9 gives us the very unlikely 1 in 90 chance of getting 2 greens. And then to get full marks we need to add all 3 of those together, which is going to give us 26 plus 1 is 27 out of 90. Now you can, if you like, spot that 9 goes into both of those and say that that is the same thing as 3/10, but that is full marks. And 30% you could do if you're showing off, or 0.3, but it really doesn't matter. Except something does matter, doesn't it? Because 2 times 1 isn't 1, it's 2. So that would be 28 out of 70, so it wouldn't simplify to 3/10. It would simplify to 14 over 45 for what it's worth. But yeah, it should be 28 out of 90. Any little mistakes like that, you only lose 1 mark for. Now, I will do question 5 next time, I think, because it's a question worth doing. But the question I'd like you to upload to me is question 7, which you can't see quite yet. The final question we're going to do for today is question 6. So you might want to just make a note of this information, but we're going to solve this using a Venn diagram. And there's 3 different drinks. So the Venn diagram is going to look something like this. It'll be 3 loops. So we'll have a 1 loop for hot chocolate. Now notice it, just have a skim through of what's going on. I can see that everyone likes at least one of the 3 drinks. So we're going to have various zones. So we're going to need loops where they all cross each other. Now, one thing to say, when you are drawing these, make sure that you get a big overlap. Otherwise, you have some regions that are really difficult to put the numbers into. So you don't, the region for just the thing on its own, that doesn't have to be bigger than all the other regions. You don't really want it to be. So anyway, the last one there is coffee. So we've got hot chocolate, tea and coffee, and we will then put what's called the universal set, which is generally a rectangle going around the outside, and there's a funny sort of E shape that we talk about for that. And we know that there's 50 people going in that. So all the numbers in here must add up to 50. So we're going to have a number 1, 2, 3, 4, 5, 6, 7, 8 for people who don't like anything, but it says every person liked at least one of the drinks, which means we can put a 0, and you normally put a line through that to show it's an empty set. So numbers are going in the rest of it. So that is, we've dealt with that part of the question. 17 people like all 3 drinks. Well, that means we can put that in there, definitely, because there's no other place that could go. However, what I'm not going to do is write 31 here for hot chocolate, because if I did, if you added up all of these numbers here, they're going to come to way more than 50, and these numbers have to add up to 50. There's only 31 people who like hot chocolate all together, and we've already got 17 of them. So I could put, if I put a 14 there, that would mean that there would be no people who like hot chocolate and tea, and no people who like hot chocolate and coffee. So I'm only going to put numbers in when I realise what they can be. So I know that this, and this all add up to make 31. I know that 17, this, and this add up to make 34. And similarly, we've got 4 numbers adding up to make 21 liking tea and coffee. The next part is more useful information because it's specific. It says 7 of the people who like tea, 7 of the people like tea and hot chocolate, but not coffee. So they're not part of these 17. And it's saying specifically 7 people like tea and hot chocolate, just tea and hot chocolate. So I can put 7 in there. And then it says 2 people like coffee and hot chocolate, but not tea. So coffee and hot chocolate is here, 2 like that. And now I know 3 out of the 4 regions I need for hot chocolate. So if I add these together, 7, 17 and 2, I get 9, 16, 26 I reckon. And 26 plus 5 is 31. So there must be 5 who only like hot chocolate. Now, what we have got left is 3 spaces to put things into. There's 2 unknowns on each one, so we're going to have to think carefully about this. And it's always good to go back and read it again. It says here that 21 of the people like tea and coffee, And I now know that 17 like all three. So that's tea and coffee. This is also tea and coffee, because tea and coffee is that bit. So 17 plus 4 makes 21. Once I know that, I know 34 people like tea. So if I add those together, that's 24. Plus 4 is 28. So 34 take 28 is 6. And now, before I can answer this question about how many like coffee as well, if I add all of these up, I'll know what's left over. I've got a shortcut because I know that this all adds up to 31 because I did it earlier. 31 plus 10 is 41. So 50 take 41 equals 9. So we've got 9 only liking coffee. So the probability they like coffee is going to be these 4 numbers added together will give us how many like coffee. So 17 add 2 is 19, 23, 32. So 32 like coffee out of 50 altogether. So that is my answer. Hang on, that's my answer for the first person. But if you imagine you had a tree going on, and don't worry about most of it, but you've got liking coffee, or in fact, if you've got liking coffee, not liking coffee, like, not like, you've got 32 out of 50 for the first person, and you've got 18 out of 50 for not liking it. Then when it gets to the next bit, this is the only bit we're worried about, liking is only going to be 31 out of 49. So the probability the first person likes coffee is 32 over 50. The second one liking coffee is 31 out of 49. And that's what you pop into your calculator. And that gives you 496 over 1225. And you can turn it into a decimal if you like and round it, but what's the point? I mean, that's just a lot more work, isn't it? So 496 over 1225. Right then, very quickly, because I'm aware I've run out over time a little bit today, but when you're having fun with probability, this tends to happen. Question 7. There you go. Pause the video and copy it down if you haven't been able to print stuff off, and give that a go and upload your effort at that to me. Cheerio, everyone.